be more comfortable. They might sound a little bit that you are not speaking in a microphone, but it works for the recording. So.
That's for the recording. Yes.
Two mics. Okay.
This is only for the recording.
Yes. So only we will be listening to this.
We can thank you. We can start the song. Is it working?
Yes. Apparently, we can sing in the rooms. They should not. So we have put a link. This is for you to register to the Pangeo EOS, which is an infrastructure that is free that we will be using. I don't know if there is someone else coming.
Yeah, we wait for.
You leave it open now. If you hear any noise that is too much, just close it.
Okay, perfect. Thank you. So welcome everyone. I do it again because it's for the recording. And can you see it, or is it too small? Yes. And there are some instruction in. So if you go here, there are some instruction about registration to Pangeo EOS. But I leave it for a few minutes. Like maybe I take the link. So that is not this one. That is not. Is it this one? Yes. It's registration. Yeah. So you will. Then you have the registration to Pangeo EOS, and this is what we would like you to do first. But I put it back. And we should receive emails when you start with, and maybe you just add, make sure you add a sentence saying this is for BiDS'25, so it's easier to identify you when you register to the platform. Am I clear or totally unclear? No, but the microphone is only for the recording. So you don't hear I'm talking with a microphone, but that's what they told us. So it will look very weird, but we'll do that. So if someone has a question, we need to come with a microphone, and you talk with a microphone, even so it doesn't look like you talk with a microphone.
I have the microphone for the question.
Yeah, yes. Think about it twice before you ask a question. Yes, so you have to request access. Yes, and you have a box where you can ask. You can write a message. Put something about like the tutorial for BiDS'. And then we know it's easier for people also offline, not here in the room here, that can accept. Once you are registered to this platform, you have access for free, like for a year. And then you will be asked to renew your membership if you want to continue using it. These are free resources provided by the European Open Science Cloud. So it's for academics and for all your collaborators in Europe and outside Europe, but with some restriction on the countries that are not allowed to access European infrastructure. Oops, this is what we had yesterday. After a while, it doesn't work anymore. No, let's see. Ça a fait ça et ça marchait plus. It's coming back. You don't see the memberships, no? Did you manage to take the link here? Everyone? Okay, perfect. Because we need to check the emails. So we have emails. No, it's not this one. What? normally. Should get some more. If you have any trouble to register, please just raise your hand and we have people that can help you around. First, I don't see. I don't see your. Yes, yes. And you don't get it? Yeah, it's a bit slow. I mean, once you did like the first steps and everything is in place, we can start maybe presenting a bit, and then because at the beginning we have to explain you a bit what it is about, and then we can come back after. Any issues to get something? All working? You want to share? Or what do we do at the beginning? No, I have this. I can do this. This is stuck. You don't really need to do the. I'm sorry. Yes. When you register, we have like 2 steps, like with a min.io. We don't really need it at for this course, but it's good to have when you want to use the infrastructure afterward. So once you have done like the first step here, let us know. So this is really registration to the cloud infrastructure. Yes? Yes. Yes. What?
I click on this one, right?
Yes.
And then I end up basically here, but I don't.
When you enroll, has it changed maybe something? Shit. Shit. It's not the right one. Yeah, because the link is maybe not the right one. Sorry. I should put it somewhere. I think they changed the link for the enrollment. That's why. Why can't I get? So the easiest is to go.
It's not yet authorized.
Yeah, yes.
You have received an email.
Okay, this is then. Did you get the info? Okay.
So the last link, which is similar at the beginning, but you have Pangeo EOSC/user/user getting started. It's probably giving you a better link for the enrollment. This one.
On
once you're enrolled, you have to go back to the Pangeo
Yes.
cloud link.
And I don't know how to share this with people.
Yeah. So do you receive an email from him for him? Who is on the first page? Who is on the page with of the cloud, Pangeo cloud? Maybe it's written not yet authorized. Who have this problem? Okay, one. And is it okay for you now, Alex?
So if you look at this is to enroll the Pangeo. Oh, sorry. This is a link to enroll to the Pangeo, and this one is if you want to get the what?
The documentation is really confusing. Maybe you could just show on the screen what we should click.
Yes, but it's just because the screen says enrollment.
So I have this account now, but I actually don't know what to do now.
So you have the EGI account. So it's a
here.
European Open Science Cloud. So when you have this is what we want to explain afterwards. The European Open Science Cloud is an initiative at the European level to federate computing resources and storage, like different services for education. And they have like a unique or federated way of authenticating yourself in all these different services. Okay. But to get access to it, you need first to register and get an account, which is what we do at the very beginning. And this is what we call the EGI check-in account. So once you get an EGI account, you can potentially request any access to any services on the European Open Science Cloud. That's the first step. Then for each service you want to access on the European Open Science Cloud, you need what we call to enroll to this organization. And this is the second step. So the first step is to get an account on the European Open Science Cloud, which you can use for any services to request access. And the second step is to ask for access to this service, which is a Pangeo EOSC. Is it a bit clearer? Yes. Yeah. So this is the enrollment access. But if you go this one, which is Pangeo EOSC instead of BiDS, /user hyphen getting hyphen started.html. I mean, please raise your hand if you need help, because we can. Did you get a AGI account? Not yet. Yes, getting started.
Some people got, but they have no access.
Yes. Apply. No. Where do we get the? Oh, sorry. They keep changing every week. No, yeah, but then it's normally, so it's, why do they change? This is to get access, it's ai.egi.eu, I think.
Okay, I have some stuff.
Let's try this one, just this one. But this, if you have GitHub, you can. We usually recommend to use ORCID, because ORCID identifier is unique for each researcher, and you can have it from when you are moving from one place to one institution to another. But you can also use it with GitHub, but some services are not working well with GitHub. But try it. And you can always link all your different accounts. Yes, and then you ask for member, and there is a box to access.
Are you member?
Yeah. Then we have pending approval, Tina.
I upload the two right now.
Yes. So can approve them?
Yes.
Did you manage?
There's Alexandre approve.
So you can, instead of, so you have an account, yes. So then it's fine. Then, can someone put, I know I need to put my finger. Sorry. Yeah, but maybe it's not.
So and now I'm approving
come back,
Gonzalo.
No, it doesn't commit.
Then you need to enroll to the service. Yes.
Yeah, that's what I've had before.
If there's anyone have problem for getting the
Yes.
Showing a different
Yeah, no,
result.
it's because now you have an account to the EGI check-in, and it takes a bit of time. Yeah,
Who have
and then you
access
ask
to
to
the
be a
Pangeo?
member. Here you
Okay.
just put BiDS'.
Who doesn't have access yet to the Pangeo EOS?
They are working on it.
Just click yours, so maybe, yeah, so you should have it. And then I clicked yours too. So you
still get support.
Huh?
You still get a forbidden.
I just clicked OK, so it should be fine.
Yeah, but you need to wait and a bit, and then be careful because you have like cookies or things. You need to clean everything if you get a 4 or 3. So wait a bit before trying to access like the infrastructure. Wait for us to accept your membership. So now you should have one more, no? Yes, it is pending. So wait for approved before going to. All good?
So who
Okay.
doesn't have yet access
But
to
do
Pangeo
you
EOS?
need anything?
And then no one is
Do
helping.
you need anything or any links or? Okay, perfect.
So that means everybody could access to Pangeo EOS right now?
Did you approve, Tina?
I did approve, so I think it should be fine.
If you refresh. Yes.
So I got the one from
Yes. Okay.
Massini.
Ouais, c'est chiant, je suis désolée. Mais
So please, who still have problem? Yes?
Yeah, but the forbidden message.
Log out
You-
and log in again.
So when you have like 4 or 3, is it what you have? Yeah. So it means, and you got approved. So you tried too early before. So we approve, and normally you access after the service. But if you did a bit slightly asynchronously, you will get this 4.3. Then you need to make sure you clean everything in your cache, because otherwise it's always giving you back this 4.3. Okay. Yes. Maybe. Perfect. So all good for everyone, or? We don't need the towel right now. So who has issue? Shall we move on? Yeah, tick, perfect. All good? So we move?
Yes.
And we'll come back later maybe on this.
And if you have any problem, don't forget to wait a hand because they have Eustace and Etienne and Aura, 3 persons who's helping today.
So what do we do? Maybe we don't waste too much time. Just quickly. Sorry? Yes, there are of course resource limits, and so it's a bit like infrastructure as a service. And when we do a training, we say approximately how many users we will have, and they increase the capacity or decrease the capacity. But we have a fairly large number of resources, and we also have storage. It's all for free for research, for education, and for your day-to-day work.
European.
yeah, European plus all your collaborators. But as I said, this is the same rule that applies for any of the probably your university resources. There are some countries like Russia, we are not allowed to have Russian collaborators. So just be aware that there are some restrictions. We just want to, who knows what is Pangeo?
Who never heard about Pangeo?
No one, okay.
No, one.
So just briefly, it's a community. It's a worldwide community, but we are quite active in Europe, and this is also why we have this European infrastructure. We are like more or less volunteer, where we are trying to set up an infrastructure for research, but also for trying out new things. So for instance, if you have things you want to try, this is usually an infrastructure where we can try different new packages or new images, new whatever. So it's what we call this culture of collaboration, and there are many like logos, but not all the logos. We only put here like some logos from the European side, and when they, whatever you teach, you usually change this slide and highlight the logos you are close to. And this is mostly because we have too many people contributing to this community. So one thing that is important, and maybe then I can skip later on, this is what we are interested in is to have something which is not vendor locked in. So it means we want only to have open source. Everything should be able to be running anywhere from the laptop to the most powerful HPC. And the reason is we want people to teach them how to do scalable data analysis. You can prototype on your laptop, and then when you are ready, you go to the cloud or you go to a larger infrastructure without changing a lot your code. This is not a new paradigm when you go, for instance, to the cloud or to the HPC. We have different like modular components in the platform, like the user interface is usually from the Jupyter ecosystem. I believe you are all aware of the Jupyter ecosystem. And this is usually through like Jupyter Lab and BiDS'. Then you have the data model with Xarray as a main entry point for like the data model. And we have like Justus is one of the developers of Xarray. So you have people from the community really actively contributing to the open source software. And then you have what we call like Dask or Spark for scaling, because we need to be able to do like this data analysis at scale. And then the rest, like storage system and resource management, so it will be different if you are on the laptop, if you are on the cloud, or if you are on the HPC. And this is usually layers here, the storage and the resource management, which as a user, you don't bother too much. And I think that's it for, we can skip the other one. Any question on this? So then now, the goal of the first Jupyter Notebook is really to try out the infrastructure yourself. So we hope you can now connect to the infrastructure. And here we have put a few like packages and like a notebook where you can try the most common components from the Pangeo ecosystem, which are probably components that you know very well if you are doing already Python data analysis, like Xarray, which is what I already here, like the Xarray, and then later on you have how to access the different coordinates, some visualization, and I see Konstantin will recognize some of the stuff we do because this is an example from us. And then another part which will be more on how to visualize and then how to access with catalog. So the idea of who has access now to the infrastructure? Okay. So the goal here now is to really try out and ask questions. At the very beginning, who doesn't know Xarray? Everyone knows Xarray? So it means for this Jupyter Notebook, it should take about 5 minutes probably to use it. So the idea is that at the beginning, we can access one file. And this is very easy. When you access one file, the only thing you need to know is where the file is, which seems very easy. But in practice, it's not necessarily the easiest way to access data. Because if you need to know where the file is on the cloud, you need to know the full path, or like a pattern, which is what we do at the very beginning here. And it can be a very long path. And it's fine when you have one file. It's fine when you have several files. But if you are searching for some dates, for some geographical area, this is more difficult if you are using directly XRE. And this is why the idea we put at the end is we explain you how to use XRE, which you can do very quickly if you know well XRE. And then the goal is when we want to do more than accessing one file or a few files, or you want to do some search, instead of using XRE directly, we are using XRE, but via Stack, which is a spatial temporal data asset. And that's a way to organize the data in catalogs. And this is very powerful because then you have like the findability of the data. You can search for geographical area, you can search for dates or for a range of dates, and you can also search for data when you have no clouds or few clouds, etc. All the metadata we have, for instance, with Earth observation data. So who knows Stack? So if you don't know Stack and you know well XRE, you can jump to this part. One thing to remember well is this, like this image. You have a catalog. So when you want to use Stack, the only thing you need to know is not the individual file names and their location. You need to know the name of the catalog. Once you know the name of the catalog, which is here, then you can search and access different collections. And for collection, we have different items. And at some point, you have files, but you don't care about files in catalog. You make some search, then you use XRE to access the data, and it will return what we call a data cube, which is mostly XRE. Any questions? So try it out, and we give you a few minutes to try this one. And I think then we can move to the next Jupyter notebook afterwards. If you have any problem, raise your hand. Oh, yes, sorry, I forgot to say. That's a very good point. So for the image on the Jupyter Lab, because you have different images, you can select for this training either the PyTorch, which we will use afterwards, or the Pangeo image.
Pangeo notebook. It's
The Pangeo notebook. Yes.
It's like a third one or fourth one.
Yes.
Can I show it in the screen?
Yeah, we can show it. You will show anyway after, no?
Yeah.
The best is maybe to shift computer.
Yes, exactly. And once you are in one image, so you select, for instance, a Pangeo notebook, you can always switch for running another notebook. You have to shut down your Jupyter Lab, stop your server, and start a new server, and select another image. You can also put your own Docker image if you have like a set of packages you want to use. Yes, that is this one. So we will use this one for this notebook, but then I think afterwards we will use PyTorch.
No, you
So
use
you
the
need to
PyTorch.
use the microphone.
No, I don't use the PyTorch. I mean, we can.
No, not you, but Mohamed is using PyTorch.
Yeah. So I guess everybody knows how. Who never used a Git clone? So you just need to, make one. Whether you use this Git app on the left side, and then like clone a repository, or slightly bigger.
Is it readable from the back? If not, you come to the front.
BiDS' zero test. So you can maybe, like, for example, go to. For example, like maybe you can start a terminal, like click here, and then you have a terminal, and then you can, for example, make a directory for the test or whatever. I mean, you don't have to, but I have so many directory and I have so many mess, so that's why it's like that. But you know, I cannot talk and then I'm sorry. And then you can just do the git clone of this repository, which is here. So Pangeo BiDS, and then you can just go to code, HTTPS, copy this, and then, are you following? Or am I too fast? Or is it fine?
So we only need to do this if we don't want to do it in the...
If you want to try,
In the Jupyter notebook or locally?
huh? Everything is there, Jupyter Notebook, and everything is there.
Don't also in the Jupyter notebook.
Yeah. So if you clone this repository, you have all the notebook that you can try, the one from the beginning to the end. So the part of Mohammed, and the one of Jean-Marc, and one of Anne and mine. So once you git clone it, so you go to the Pangeo, the directory, and then you go to the docs. You go to the docs directory. So you can BiDS test. No, it's not. No, Pangeo BiDS, yes. Pangeo BiDS. No, I think I didn't do it. Tell me if you have a problem for git clone. And wave the hand, because we have Etienne and Aura also to help you. Okay, so once you do git clone, the notebook which Anne was showing is in the docs folder called intro. So you just need to like run kernel and run all the cells to be lazy, or you can run it one by one. And then if you want to switch between the cells, it's nice to click this 3 lines here on the right. And then with this, you can easily like switch between the cells. And then also, like if you go on the left side, you can also click the chapters, and then you can also jump between the chapters. And there's a data from sample service crashing. Sample service, pass to the sample service is not working. A backend is not installed. You have to put the backend in the original of the main.
I forgot to add you need to install
Yes.
XRA-EOPS. I'm sorry, I forgot.
Pip install XRA EOPS.
And this is a good exercise to show you that you can add packages even if you have selected one image.
So, yes, it is. Yes. Hello. So let's go back.
If everyone is ready,
No one complains.
So kernel, restart kernel, and run all cells up. Oh, well, it will do people install again, but anyway.
you can click on the double triangle.
Oh, I didn't know that, John Mark. No, I never used that one.
Ah, yeah.
So now we can load the data with engine EOPF ZAR.
Yes, because I took the Pangeo notebook image and I used the PyTorch.
Nice. I like the color.
Yes, yeah. So you when you install a package, always restart the kernel because otherwise you are in between. You install something, but if they change downgrade or upgrade some packages, it will not work. So thank you, Tina. Sorry for that. So always, every time you do a pip install or mamba or conda install, always stop your kernel and restart it and rerun all the sales. Then it should work. Yeah. That's the second lesson learned. First one, you can install new packages. Second one, when you install a new package, you always restart your kernel and rerun the cells. Restart? No, I mean, and ideally, that's a good point. So normally what I do is, this is like prototyping. You see you are missing a package, so you add it, and you make it, normally you should put it in the notebook here, so you know. And then you create a new image with all the packages and the pin version, so then you can give the Docker container to your colleague, and it will be exactly the same. Yes, you can, exactly. So you use the environment file, you can create a new environment file, and then you create a new Docker container, and you put the image public, and then someone else can reuse it. That's the best approach. Yes? You need the microphone.
Okay. What do you recommend if my colleagues work with Windows, how they should use Docker?
You can use Docker with Windows, and there is no problem.
For the colleague Windows, I have answer.
Yes? Like the virtual, like the app. Yes.
I am working
Yes,
with
yeah.
Windows.
Yes.
I am working with Windows.
So you
in
are
fact,
using the app, no?
no, I'm using WSL.
You are using WSL.
And you have the Jupyter notebook, something like that. So it's exactly the same way than Ubuntu, and it's working very well. I mean,
yeah, but
I have
the
no problem.
Docker on Windows works. It works very well.
No,
Yes.
it's
I think it would be nice. I think it would be nice. Like we update the Pangeo installation website. That also details how we use the WSL. I mean, we have one for internal website in our lab, but maybe that's something we can push it to the somewhere of a page because it. Yeah. But there are some versions, or there are sometimes like when you want to link with GPU, there are some tricks and so on.
But this is to run in local. For Pangeo, you don't care about all this.
I mean, Pangeo EOSC.
Yeah.
Pan-
No, but in general, Jupyter notebook are very.
Students in the class for testing, then the cloud infrastructure is the easiest. So like whether you use a Pangeo EOSC or you ask. But for operational courses, I mean, if the university can also give you the Jupyter Lab access, like if they can install Jupyter Hub in their cluster, that would be the best. Yeah.
So that's why we have the European Open Science Cloud, because some universities are better served than others, and especially small universities, sometimes they don't have the capability and capacity or infrastructure to deploy Jupyter Hub. While at the European Open Science Cloud, we are federating resources, so everyone is putting a bit of resources, and everyone can access it. So it's more like equitable in terms of access. Like, for instance, I am in Norway. Nobody cares about the European Open Science Cloud because Norway has more infrastructure and they use the local infrastructure. But then when they go abroad, they don't understand why they cannot do their own work exactly the same way. So it's good also to learn how to do it in this more European. Yes, exactly. Because here there is no vendor lock-in. If you are running it on the European Open Science Cloud, what you run here, someone else can run exactly the same. It's not dependent on your local setting, where you have no control on the image, etc. All good for this notebook? No? What is wrong? Yes, but it's good enough to do what we have to do constantly.
No, it's not. It's the CRCR1. It doesn't have anything in there. And now I'm trying to select.
No, we all managed to install it with pip.
We used it. Okay.
Yes. Yeah, because I think there is no, yeah. If you use pip install it, yeah, some packages, something also to be aware, some packages are only in Conda, some packages are only in PyPy, and some packages, they have different version on PyPy and Conda. So it's something to be aware, especially packages that are under development. Usually, if the developer has a preference for one package manager over the other, they always a bit shifted. Yeah, you need probably to upgrade if you install an old version. Capital or hyphen upgrade. So who else has trouble with the first notebook? All good? The first notebook was mostly to try out. It's okay, don't bother. Yes. Restart your kernel. And this is a very basic notebook, so we don't need So I think, Tina, maybe you can start the next one.
Yeah, because otherwise we will not have enough time for Jean-Marc's part. So I just want to talk about two points. So in the notebook that you're running, in the end, there is a part which is explaining about the chunking.
It's a tutorial.
Who knows, who thinks you are the expert of chunking? So who never heard about chunking? You guys all heard about chunking, and you guys are super like annoyed with chunking sometime, or like puzzled with chunking, or like I'm using it, but I'm not sure what I'm doing is right, or I don't know. So, yeah. 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 Exactly. Yes. And yeah. So this. Okay. So this part, like we're gonna talk about chunking, as you know, that the spatial chunking and time chunking, which way is the better, and so on. That's really depends on what you want to do with your data. So this one, it's I know I had one graph is that spatial chunking, and then anyway. So this one we have the X and Y. And then the time. So this one, it is chunking on the size of time. It's X and Y. So in a sense, it's a like data cube. So it is not. It's not like a lasagna type, like sliced time chunk. Am I clear? Right. So and then this is more like what we call a ravioli type chunk on the right side. So there is also like you can do the spaghetti. So you can do the one line from here to there. You see, like you can have all the time series in one chunk, but very small X and Y. So you cut it in a very small here and so on. Where that's for time series. But in my point of view, if it is sort of cubed in the data cube style, afterwards you can stack it so that, you know, if it's small enough, the data cube is, then we can have some sort of stacked for the time series or stack for the all the slice, the lasagna way. So like in my point of view, like ravioli type is the best. But so there are some like data provider who is trying to do this. And one of the example that I will show in this notebook, so the notebook that we prepared is called SSD_AI IPyNB because it used to be a SSD and AI notebook from Igers, so I forgot to change the name. So there is no AI in this one. The AI part is
It's coming after. Yeah.
So if you try out this notebook, so you can also try to start execute this notebook, like all of it with this button.
You will show the Dask.
No, the SSD_AI.
You don't have the Dask?
Yeah,
You will
there
show the
is a
Dask.
task inside in this one.
Yeah, but to show the Dask dashboard.
Yes, I will show it too.
Okay. Okay.
But it's in my head.
Yes.
Yes.
No, it's just because Jean-Marc said he will also
Yeah.
show.
And then I do the restart the kernel, and then so it will install several packages, XGS, Copernicus Marine, Helpix, and so on. So the part of Copernicus Marine. So if you look at this part, so I will talk about Dask later. But so if you look at this, so the chunking. So there is, in this Copernicus Marine service, so they provide geo-chunked ZAR and time-chunked ZAR. So that's like for the certain, so they provide this lasagna, no, not lasagna, lasagna style, like all the time series in one sheet, kind of like a time-chunked ZAR, and then geo-chunked one, which is a bit like ravioli type, the one I showed.
So this is like Latlon
Yeah,
for the first one and one for time?
Yeah.
Or?
Yes, this one, the figure that I was
Yeah,
showing
okay.
before. Yeah. So so it's so for example, if you want to do the time series analysis, it is important that you have all the data for the time, right? So before that, you probably need to re-chunk it so that you have all the time. And then if you need to do the spatial analysis, it's better if you have this data cube time. So depending on the situation and also the chunk size, it also differs.
But so can you explain why it's important?
Why
like for
it's
the
important?
memory or
So-
for the scalability? Or?
Yeah. So why it is important is because we want to treat this data in Dask in parallel. So when you do it with a Dask, that means Dask will know where are your data. So Dask, if Dask thinks these two data in the different chunks, when they execute their calculation, they will try to get it by themselves. But sometimes it's not really optimal. So it's easier that you indicate the Dask that I want to stack this data in this way before you run your calculation on the part of the Dask that you need all these data. So that's why it's important just not to let Dask do everything that you want to do, but you need to think a little bit in the head and in before, like, and say, I kind of reorganize my data in a sense that it fits on the calculation you want to do. So that's the message that I just wanted to pass with this image. And then I'm coming to the Dask part. So once you run this notebook whole through, like you might need to run it like twice because there's a pip install. What you can do is like so wait. So you have the you can launch the Jupyter Lab on the right side by clicking this. And then as it is indicated on the dashboard, so you click left side. And then here, if you are using your Node PC, here that it is, or that you can keep it as it is. But as you are using the cloud.
The cloud. Yeah.
So you need to change this to the proxy status. And then as you see on the right side, you have the different workers popping up. And yes.
But this is all explained. Huh?
Yes.
So if you have any problem accessing like the Dask cluster, please raise your
This is
hand.
the key. So this 8787 is the number of your Dask here, the Dask process. So you need to indicate this 8787 and also /proxy. So, and then this notebook, so that this was an example of like if you use the data from GeoChunk or TimeChunk, but unfortunately we had some problem of loading some data from Copernicus services. So I switched this example so that it use data you can get from Iframea server. So that's why there is it's doing this twice the same thing. And then, yeah. And then, so afterwards, you didn't talk about this attribute and so on, right?
No, because most of them said they are familiar with,
Okay, so I
with
will not-
XRA, but you can mention it.
Yeah.
And
So-
if you have any question when you execute the notebook, the main goal of this notebook is to see like the parallelization and
Yeah.
the remote access of the data.
Yeah, yeah.
And then you will convert in to
Yeah.
a different grid.
So in this example, so we are loading some of NetCDF file, which is stored on Inframea server as a product, which is the same data as the Copernicus Marine Services, because we are making this data. And then it's just because I want to load like 10 files at the same time. And so I use this file list from the globe. And then we use OpenMF dataset, and then take all of that file, and then decide the chunks, the size of the chunks.
So here, this is where you see having a catalog would have been more helpful, because you need to know the pattern and where the file is exactly. Well, if you had a catalog, you would only need one line for the catalog. So just.
And
so do
also-
you manage to get this, or? Yeah, you are supposed to run it yourself. It's a tutorial.
I said click this button.
Yes. Yeah. I think it's good if you try it, because this is exactly how you will have to do it when you want to parallelize with Dask.
Yeah.
So just make sure, ask as many questions as possible or what
So
you do
as
not
you-
understand.
Yeah, as you can see, like this OpenMF dataset, you see there's several parallel processing, process running, and then doing, for example, open dataset in parallel, and then afterwards concatenating the file, or for example, it is also doing here like a lead chunk and merge, and the different processes that I didn't write here. I only said open MF dataset for the group of file, and then it does it automatically behind. And here I said that I want to chunk with a time equal 1, which means that if I look at the data set here, you click this small data, and then you will see that time you have this like very small, just 1. And then on the latitude or longitude, I told that I want the latitude as automatic chunk, and longitude, I want it as 10 mega maxi. So that means they didn't.
Tina, some people, they need to put the username and password for Copernicus.
You can skip that cell.
Okay, so just take the next one. Ah, that's the one, yeah.
That's the one which didn't work, but I kept it because they are having the geo and so on. That cell, you can skip it because the cell next that
Yeah, but you need to stop it. Yeah, yes. Yes.
To skip
So
it and
if
go
you
to
get
next one.
to enter the Copernicus username and password, you need to stop the cell and to go to the next one. Are we clear or? Yeah, you need to stop the cell. There is a button, the stop button.
And then you don't need to restart it.
Because if you restart and you execute everything, it will be the same problem. Yeah. Any problems? No? All good? Perfect.
So if you have any problem, Etienne and Aura, you can walk around and maybe see the people if they have
So
problem.
here you don't see anything because you haven't put yet. Did you follow the instruction for the Dask? Yeah. Because here I don't see.
So as you can see on the
because it's
next one, like
something-
analyze
yeah,
the
because we
SSD,
didn't
you
execute
you
it yet.
click this
You go
this
down.
part, and then you
So
will
this
see
one,
how it is chunks, the
skip
data.
okay, and you did this one.
So
this one,
if you want to
where is
limit the memory
cluster?
and so on, it's nice like you when you open it, you just define it there. So to see what kind of attribute you have, you can also, for example, load this L4 analyze SSD and then ask for the attribute. And then you will see like a standard name or units is a Kelvin and so on. And then if I go to the next cell, so what we can have with this kind of attribute is very useful. Like for example, if you want to convert the units, in this case, the units was Kelvin, but we want to put it like a degree. So by using a pint, and if you have any question about this pint XRA, ask Jean Eustace because he's a developer of it. So we can, for example, use this kind of attribute to convert the unit. So what I'm doing on the next cell is like, so I convert to the degrees Celsius, and the attribute is updated automatically. And for example, I can persist the data, and then as you saw on the right side, like you can see it's persisting, so you have more memory there and so on. And then if you want to write this data to ZAR, you can say the name of ZAR file. And then if you, so as you can see down on the right side that it's the calculation is running. And then if you want to see what is exactly ZAR is doing, you can look in the ZAR folder like that, and then you can see, I don't know, you can see up. You can see inside. See inside the directory of ZAR, basically it's a lot of chunks. So you can have see the different chunks and so on. Because I installed the EOPF, my ZAR is a version 2, Constantine. Because I think I did a pip install EOPF, my ZAR was a ZAR version 3, and I think it pushed my ZAR version down to 2.
Yeah,
Yeah.
because one limitation is that we need to use
Yeah.
that too. Sorry.
No.
Because of our other project.
So it's not the ZAR JSON.
Yeah, yes, that is true. That's a metadata already. Now you have the one.
Okay, I think I will go on because otherwise there will be not enough time for Jean-Marc stuff, and I think that would be pity. So basically, if you have time, like you can run it and see, like try the HV plot and so on. And then I will just come to the introduction for the next part, which is talking about hill peaks. Who have never heard about discrete global grid system? 1, 2, 3. So who thinks who doesn't so I will go. Okay. So discrete global grid system is Alex is gone. Oh. Okay. So if you have a question about the theory and so on, go to talk to Alex. And then anyway, and then it's a global grid system. It's like latitude and longitude. This is not a good slide.
So, but can you explain why you want to regrid the data? managed to break it.
So why? Because we have the latitude and longitude grid, and then each of the grid size is not the same size. So when you want to do the statistic, it could be cool if it's the same size, and then you don't need to multiply the weight factor, and then it's, you know, I mean, when you download the satellite data, they use a UTM, which is not that long, and it's not even same shape on the size and so on. So that the idea is, can we have a better grid system? And then if everybody can use the same grid system, when you compare the model and satellite or different models and so on, it will be so much easier. Like for that's the idea behind it. And then we are like Anne, Eustace, and Alex, and Jean-Marc and me. We are using one of these grid systems called HealPix. For example, other DGGS example, there's H3. Uber made their own DGGS because for them it's much simpler not use that long but make their own grid. Or Google have S2. So different. So there are so many. But us, we chose HealPix because for us, the HealPix had the best property because it has a very equal area for compared to other grid system, H3 or S2 or other different thing. And then also it's been used, it's developed by astrophysics, right? Astronomy.
That's not why we took it. Huh?
Cosmology. And then they have like 20 years of experience, and there's lots of like Java, C, or Python. There's lots of developments around, and there's also another reason why personally I like it. Well, I will go on it to later, but anyway, globally, HealPix is like it's divided, the surface is divided in 12, and then once each of the cells, like a face, this part, is divided in 4, and then afterwards it's divided in 4, and then it's divided in 4, and 4, and 4, and 4. So it's, if you are there, and then you know what's your parent cell, and then it's your grandparent cell, and grand-grandparent cell. So it's like if you want to do the mean and so on, it's very simple. You just need to add your brothers and sisters, and then you can do the mean. Yes. Yes.
Yes, and this is why this is super important, because especially if you are high latitude, if you have a cell that is a different size than in other part of the globe, when you do your averages, it doesn't work. And when you do AI, it's totally wrong, because you are training usually on data that are on the equator or like a very nicely area, where the size of the cells are more or less all the same, and then you are trying to apply to a high latitude where the cells are completely different sizes, and then it doesn't work, and people don't really understand why it doesn't work and why they need always to multiply and add more entries. Right. And this is exactly what Jean-Marc will explain, I think, in the next.
It's the same equal area. It's very important. So it's not the size, because the shape changes a little bit. So it's a surface. It's perfect. It's
Look at so for example, the first to 12 cells, and then we call it a level 0, and then so it's like go by to 4 times. An example of Jean-Marc is, for example, using level 19, which is about the same size as 12 meter. For the size of the cell, which is about UTM 10 grid over Sentinel-2. And what else I should say before I go away? Yeah, and then so this level is the term that you would hear. Did you use inside or level? Level. Okay.
Sorry,
and then and then inside is the way that the astrocosmology people call it, which is just 2 to the power of a level. So it's the same thing. And then in this example, it's just fitting, reorganizing this lat-long data on level 7, which is about the size of 50 kilometer grids. And then just reduce the mean group by and so on. But there are now we have lots of nice tools to do this kind of things. And then, so just want to tell you is like even and then in this kind of, so for example, I stop it here. So for example, we have also,
It's not available because you didn't stop.
no, I have the data. So I just need to, no, not this one, it's this one. So for example, if I open the file that I already calculated normally, and it's not coming, of course.
Too many people on Pangeo.
No. So you will normally see the beautiful slide. Like if you execute it, you will see the beautiful graph that you can also have a time sliders and so on HealPix. And it's just before I go away, one last thing. Why HealPix is good? Because HealPix is compliant with spherical harmonics. It's the nature of it. We can go from the grid cells to spherical harmonics analytical format. So when you want to do some mathematical analysis, like analytic, you want to make some analytics using spherical harmonics, you can use that property. And then for those people who never heard about spherical harmonics, it looks like that. You have like, maybe you have saw it on the chemistry like long time ago, like things like you have a sigma and the pi and the delta. No? Like clouds. Well, that's. To quoi? Yes, it's because we need, because with the HealPix, all the cells, it's just a grid value, right? But if we fit it to the one spherical harmonics, then you can express it with analytical forms, not with each value in a discretized form, but then you can have analytical form. And then you can use different, if it is useful for making different like analysis using this analytical form, which maybe Jean-Marc can explain.
In fact, if you want the full story of this spherical harmonic is equivalent to the power spectrum on the sphere. I can tell you the story during the coffee. It's Georges Smoot died 1 week ago. I will explain you why this give a Nobel Prize on the Kobe experiment. Because of the success of this type of grid to compute quickly spherical harmonics. But it will take me more than 30 minutes, so it's out of the scope of this. But with a big pleasure, during the coffee break, I can tell you the story of Kobe on spherical harmonics.
Just to check what time we are supposed to finish?
10:30.
10:30, right?
10:30. So next notebook is X-Batcher, what's the name? Sentinel-2 Wave. So it's an example of the usage of Pangeo platform to extract some poor spectrum of the wave. I'm not talking about the spherical harmonics.
If they want to run it already, they can run it.
Yeah, you can run it. It should work. I will give you. So the idea is to show how we can use X-Batcher, which is a way to do an orchestration of a small but complex operation. So I will show you how I use it to extract the power spectrum of the wave at the surface of the sea on small patches on Sentinel-2 data. So this notebook has been built from or strongly inspired from another notebook. I put the link on the this version is not the last one. Sorry. Anyway, I put the link on the. No, but it's running. There is a link somewhere on the notebook. You will see on the top, and it's also using some definition of a paper. So the idea of this notebook is to use 2 pictures on from Sentinel-2 data with 2 bands. And in fact, 2 bands is not taken at the same time. So you see the wave moving. So it gives you some information about the direction of the wave. So let's go a little bit on the notebook. So here you see in this cell, does anyone succeed to call it, to load it, and to run it? It should run. You just push the beautiful double triangle.
If I started only the Pangeo notebook, should I now start actually the PyTorch notebook, or is that not
No. You can use the PyTorch because it's using the backend is using some libraries that is using PyTorch, but frankly speaking, it's just accelerated by 40%. And the demo is very short, so.
So just to say, like when you are using the PyTorch image, we have some GPUs for you to do the analysis. When you are here, you don't have any GPUs, but for small analysis, this is more.
Yeah, in fact, to ease this notebook, I'm using specific packages, which is FOSCAT. So this is a package that is developed to compute convolution on the sphere on DGS, because you have to define specific convolution. And it's also mainly developed to do statistics. And FOSCAT is the name comes from scattering covariance. I will not introduce exactly what it is. Scattering covariance is a mathematical transform that does the same thing as neural networks without training. So this library is done for that. But it's not used here in this notebook. This notebook is just using the ability of FOSCAT to do convolution on the sphere. Real convolution on the sphere, meaning that your kernel is the same at the equator and at the pole. It's defined like that. And it's based on Torch. It was based on TensorFlow, but now it's based on Torch. That's why I call Torch. But so it works on GPU, but frankly speaking, for this notebook, the GPU will not help that much. It's more. Anyway, so I have to, as it has been said before, I had to install. So you have to install several packages. So to get some data. So the idea is the next cell. Up. So I start the DAS client. So I already started exactly in the same situation than Tina shown you before. So I have all the tasks ready. So the first thing that is done in this notebook is to call the data from a stack catalog. So the idea is to get the data from Sentinel-2. I look for a coordinate in Bay of Biscay. I'm from Brest, so it's not far from. So I know that there are some oceans here, so it's easier. And the idea is to have some information about wave. We need some elevation of the sun. So this is what is specified here. So you have elevation that you need. If you are exactly at the vertical, you don't see the wave very well. So, okay, I got the catalog. So, it's a UTM tile of 100 kilometer by 10 kilometer by 10 kilometer, sorry, with 10-meter resolution. Oh, sorry, I didn't. Yeah, because there are some compression about the reorganization of the data, so you can lose some information about the timing. Frankly speaking, I didn't.
It's also the original research workflow. It's used even L1B.
Yeah.
Not the regraded. Yeah.
Yeah, because L1B keeps some information about the detector, the real detector data.
And
you and I regrid anyway.
But it's not. It's just a
already
L2A. It's take out some information which we need because it smooths things. So that's why we need L1C. It's the same, exactly the same. But we don't use the L2A because the L2A there is putting some atmospheric the correction and so on, which is not good for our use case.
Yeah, it removes the waves, in fact. 11.1b, it's even. In fact, the 11.1b is not stored and available, and so on. So the idea, the first idea of this notebook is to convert the UTM in ILPIX. Why converting in ILPIX is, in fact, if I want the real north-south direction of the wave, I cannot use UTM because UTM pixels are not oriented, or I have to change my convolution. So the idea is to do the power spectrum of the wave is doing like an FFT, a Fourier transform of the UTM tile, but this doesn't work very well because you have this problem of definition north-south. So that's why I'm going to ILPIX. And to gain some noise, I will show you that I use, in fact, wavelet definition. Does anyone know, doesn't know at all what is a wavelet? Everybody knows very well what is wavelet.
Just a small explanation.
Cool.
Just a small comment for Konstantin. This notebook originally was made for some EOPF sample service, Webinar 6, but it is from this part everything is different because Webinar 6 we used it with UTM, but this one it's change it to ILPIX, and how we do the FFT is completely different too.
So the idea is to get first the coordinate and to convert in ILPIX. So the way it's converted in ILPIX, so I got all the measure. So this is the two data, B02 of B04, and you see immediately that in UTM you have a rotation, which is related to the tile of the UTM. So you don't have, the pixel is not exactly north-south. So you can go in the detail. I have not huge time to explain, but the main idea of the, I don't know why it's a demo effect. I have a beautiful schema to explain. So the idea of the interpolation is not an interpolation, it's an invert interpolation. The idea is to find the ILPIX pixel that in such a way that when you interpolate the UTM data in ILPIX, you have the good value. If I have a pen to draw this. My image is dead. So the idea is to have the UTM here, and you have the ILPIX pixel here. So the idea is to compute the ILPIX pixel in such a way that when I interpolate the bilinear interpolation of the UTM grid, I have exactly the same values than the UTM. It's the contrary. Oh shit. So it's contrary. Sorry. Okay, restart again. So the idea is this. So when I bilinear interpolate the UTM value, I use 4 values in ILPIX. And the idea is to find the ILPIX value that makes this interpolation exactly the same numbers as UTM. And that's the main idea. No, but it is here. It is, but it's okay, I think.
It's this one. Bilinear plot. Bilinear. This one.
Yes.
Yeah.
Oh my God.
Yeah. It's the same that the one I have done here. And in fact, I made it in the wrong way. So the idea is really to have to get this. It means that you need to invert something. And the inversion is done by a conjugate gradient function that is called from FOSCAT. And you will see in the notebook that it could be a complex task. So this complex task is localized because it's called localized with the pixel. So I can split the computation on many patches. And that's the way I use XBatcher. So here, you will see the function. Let's go inside. So count patches is just to have a beautiful, I like this, to have something moving to 100%. So this is not very important. So what I define is 2 ILPIX dask. So I will get some patch in a dask in data set, and I use this one is a batch generator. So it will split. It will generate the batch thanks to the description of the description I did. I did a very simple description. It's taking 128 patch and cut all the image. And at the end, you just process patch. So this function is just taking the coordinate, convert the coordinate in ILPIX. So ILPIX is colatitude. So you have a definition of 0 is at the north pole. So there are some few differences. Compute the weight of the bilinear interpolation. And cut if you have holes in UTM. So it may happen. So if you are at the limit of the detection, so you cut one line and you change the weight. That's a function which is done here. And I use a conjugate gradient from Foscat. And Foscat uses this very intensively, this conjugate gradient for optimizing things. So this software is a complexity of n, so it's quite fast. And I compute the two band and run it. So let's define this. Okay, I execute this cell, I execute this one. And after that, I just have to call two ILPIX dask, the level of the ILPIX data, the data set, the patch size, and the transformer is a transformer for the computation of the lat long in UTM. So let's hope that it will work. It not work. It was working just 1 minute ago. So you expect to have a... Why you changed something to my screen? No? Okay, don't worry. Anyway, it was working. So usually you have something showing that a beautiful 0 to 100%. So what you can do after is to visualize the patch. So you see that this is all the patch. So this is in ILPIX. So okay, you have this north pole rotation, but the ILPIX take into account the fact that it's rotated. So this is all the patch, and I hope that you see some wave on those patch. So I'm happy. So now I want to do the same, but I want to do something a little bit more complicated. So this is the idea is to do a wavelet convolution. So the idea is to define some wavelet kernel with a different rotation. And you see the real part and the imaginary part. And to apply to an image. So I show you what happened to an image when I'm doing this. So here is up. Here is a toy model. So this is a toy model that you can see I produced by myself in a very, very easy way. So this is a noisy part. And this is the wavelet transform, the coefficient for this and this. So what you see here is the orientation. And what you see here is the scale. So you see that you detect perfectly that you have some wave. If you had some noise by height, you don't see anymore the wave, but still, wavelet is still seeing show something. Why wavelet is working is because, compared to the power spectrum, is because wavelet is merging some information on the spectrum. And why it's working on the wave is because the power spectrum of the wave is smooth. So if you do on the power spectrum, which is a more classical representation, so you see the direction of the wave, and this is a classical Fourier transform. So this is exactly this plot, but just in a polar, in another way to plot. So if you add noise, you see this, and in fact, this is what you see in a Fourier transform. And what is also important, and you should understand in the next slide, is we use cross statistic between the two bands, so it will reduce the noise, because the noise is not the same on the two bands.
Just to add one thing, can you explain why you need to use a two images?
Two band, it's because there is a delay between the two bands. So you get the direction in the phase of the Fourier transform.
So for example, we have a B02 band and B04 band. The photo is taking it's like 1 second different. So this difference, we can have a lot of fun stuff. Yes. Yeah.
Yeah. We can. Yeah. Yes. Yeah. We can combine.
Yeah. 2 and 4 is not the best. I
No,
mean,
no,
it's
no.
Just, it's just
a
my
demo.
colleagues' MATLAB code was using 2 and 4, and then.
What is important to understand with this notebook, it's now very easy using the X-Batcher and things like that to do all the bands, thanks to the fact that you have a stack catalog of Sentinel-2, and to run this on the whole ocean part.
Maybe also
just a matter of
another thing
computation.
is because we are looking at the ocean, so the color band where we catch better the ocean color and so on maybe differ with the 2 and 4 and 6 and 8.
Yeah.
That's maybe there is some stuff, yeah.
But frankly speaking, if you had more bands on your more cross power spectrum, you refine your result at the end.
And this the difference of the how many seconds and so on, you can get everything automatically from this data tree of a new Sentinel-2 ZAR format.
Yeah.
In a stack, it's in a ZAR metadata, not in the stack. If you do the query of it, you don't see it. It's in the metadata once you open the sample. ZAR, yeah.
Yeah, yeah. And what is very important to understand with this demo is to show that we can do some complex operation and it's scalable. I mean, I can ask for all the data on ocean and it will be the same software. So for, I just want to advertise the birth of Feather about doing AI on Sphere, because in fact, to define the kernel on Sphere and DGS, in fact, you have the notion, you have the idea of gauge, orientation gauge. I will not talk about it now, but in fact, you don't define 8 rotation, you define only 1 rotation. After that, there is some symmetry on the sphere that avoid you to express the rotation. So if you want to, Anne, when is the discussion about, when? Yeah, so it will be a pleasure to explain why the spherical neural network or AI should be specifically defined, because it's the definition of using flat neural network on a sphere is completely false. So just, and that's why the kernel is defined only once. So it means that in AI, if you use the sphere, you are using less definition of kernel. So you have less parameter to train, in fact. So this is the way we are computing in detail the power spectrum. And I just want to come back to one thing: is in fact the idea of doing the wavelet is to do the wavelet as a full resolution. And instead of changing the size of the kernel, you change the size of the data. So thanks to ILPix, changing the size of the data is up. No, it's not here. Sorry. Up. It's here. Up. It's just this call. It's down. And mainly this function down is just doing the mean 4x4. So it's very easy to do a multi-scale analysis. You just do your wavelet on the one at the full scale, you divide by 4 your data, the mean or your max, whatever you want, maximal or something like that, and you do the kernel. And you loop several times, you go down in a resolution by a factor 2, and it's running. So at the end, what you get is something like that. So this is the 2-band power spectrum. This is the cross power spectrum. Let's get some information. So you see that the cross is strongly denoised. And this is the phase. So you see the orientation of the wave. So thanks to the fact that you have a shift in time between these 2 bands, you see the direction of the wave.
Can you explain what is the red and what is the blue, and how do you see the direction of the wave?
The red is the positive phase, and the blue is the negative phase.
So the wave is coming from where to where?
Top left, down bottom right. It depends of the delay between these 2 bands, in fact. So it's a matter of sign. So And at the end, this is a patch that corresponds to this. So this, I just did it. So it really shows that, okay, I think I want to do this. I do my cell, my Jupyter Lab cell. I check on some patches. It works. So now I have just to copy and paste in the middle of my Xbatcher stuff, which is here. I just add this. And now I can run it. Okay. It's running, yeah. It's running. And after that, I can show you the end. Sorry. It's running. It should be 1 minute. No. It's okay. It will come. And at the end, you see that I've designed some, let's say, complex task that is very easy to schedule and to apply to all Sentinel-2 data, so which is unbelievable. I can really push the notebook. I hope it's running. Something happened here? No, but it should not. So you can. Anyway. So anyway, we have the break. Do you have some question about this very quick and short talk about this notebook on all the other notebook?
Comparison between NFT and Wavelet. Wavelet shows better example because it passes out of noise. Is that correct?
Yeah, it's because the wavelet, in fact, integrate. In fact, if you see the power spectrum, you have some wave power spectrum is like that. On wavelet, it in a Fourier space is like a filter, a scale filter, which is quite large. So you do the mean of the value between the wavelets. So you can get about the same thing by doing the Fourier transform and doing the mean. Yeah, but the point is the wavelet is localized. So what you earn with wavelet is the fact that if you have some undefined data, or some NaN, or if you have some structure that is not cool, you can do the wavelet. So for instance, in the domain I have here, I didn't go. Oh, this you see that there are some trick. In fact, this is not a good example, but yeah, you have something here. And in fact, when I do the mean, I don't do the mean, I do the median value. So power spectrum, you cannot do that. If you have 1 point which is very strong, which is completely crazy on the full field, you do the FFT, and it will blur the FFT. If you do the wavelet, you do the mean of the amplitude of the wavelet, and it removes this. So that's why we use massively wavelet on statistic instead of Fourier transform. But this take as a strong hypothesis is what you are observing is smooth in Fourier space. This is particularly true in Navier-Stokes fluid dynamic and things like that, because on most of the natural things, because of the V grad V and blah, 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 blah. But if you do power spectrum or tide, you have to go to harmonic phase, harmonic inversion. So. Yeah, exactly. Yeah, but in fact, I could have put. Yeah, but here it's a very naive view, because I agree with you. If I do the smoothing of this, it will be about the same. But if I put a big point here and I do the median, here I will have the proper power spectrum. Here I will have junk.
A quick question regarding Xbatcher, because you brought it up. If I would have to do overlaps, like you can in X-ray, you can do map with overlap, or
it's defined.
How does basically X-ray map blocks or map with overlaps relate to Xbatcher?
I didn't at the beginning. No, it's okay. You define the overlaps. Up.
You actually do overlaps.
Yeah, but 0. But you can define overlap. For instance, you are right that if you want to do UTM to ILPIX, you need to overlap a little
Or some
bit.
padding? Or
Yeah. You have to overlap to manage the point here.
yeah, cool. Okay.
But you can define overlap, yes. So here I put 0 because I don't care because I'm knowing.
And you basically just batch along a dimension, or can you also batch along 2 dimensions?
Yeah, it's
Yeah, like you
2
do. Yeah, okay. Yeah, okay.
No, it's very easy to use. Yeah. Frankly speaking, I didn't know Xbatcher 1 month ago. And maybe 1 month I'm generous, maybe less than that. So it's really easy to use and it's scalable and it's unbelievable.
Other questions? We have a coffee break if you want coffee. Do you know where the coffee is? It's at the first floor, which is ground floor. And this is 106. We have coffee, everything, and we are convening at 11 with the next part of the
1, 2. Yeah, because I didn't hear anything. And I was wondering why is talking to the microphone. What time is it? Is it? Okay, just wait for another minute and then we start with the detection of the first. Okay. We missed one, then we'll get another one. Christina, we are down to. She's talking. Okay. Probably it's gonna come back after lunch. Okay. A quick introduction. This is the rest of this tutorial is about the work that I've been doing in one of the European funded projects. It's called EO4EU. It started almost 3.5 years ago, and it's about to finish end of November. At that time, there was a call about making the, let's say, uptake the Copernicus services. We're talking about 2021. We bid for this call, for this call. And it was evident at that time, and still is, that using Copernicus services is not that easy for, let's say, non-experts. So if even if you're an expert, combining data from different sources is because you have to log into multiple services, have different accounts, and then access and downloading your data to your PC or whatever, and then processing it. So that was the main driver of this call. We submitted a proposal. We got the funding. So So you have to scroll. So the objective was to create something that accessing the Earth observation data from various data sources, from Copernicus, Galileo. At that time, actually, as I forgot to introduce myself. My name is Vasilis Baousis from ECMWF, and my colleague also, Mohammed, I destroyed. Mohammed from Al-Baghdadi from ECMWF as well. So, and at that time, we drafting this proposal and actually start running this this project. We are drafting also the Destiny or Destination Earth, let's say, specification. So the idea is that we created a platform, the EO4EU platform, to access Copernicus data, Galileo, ECMWF also data, and Destiny. And we did that with a very combining, actually creating a knowledge graph that contains all the possible sources, and then the user can easily, let's say, query with a native language the knowledge graph and get the result and the access to this data. It's a platform. There's if you go to EO4EU.eu, you're going to find also the relevant information and the relevant, let's say, access to the platform. And besides that, there's also, okay, so I'm always so you can find the knowledge, the way to access the platform, the marketplace that exists, and the various other utilities and functionalities that the platform provides. In general, it's a platform that runs on two different clouds. One is Syneca, it's partner of the project, and another is in Wikio. Wikio is one of the DSS that still exist and is It's, let's say, it's led by ECMWF, EUMETSAT, European Earth Observation, no, European Environmental Agency, and Mercator Ocean. And we have split that in Wikio because there are some utilities there. We use Wikio, or we use the other public endpoints to retrieve data. And then we have the cloud platform that we run the utilities. So when you download the data, you can specify computation that you like, or any algorithm that you like to use from the existing platform, or you can define your own, and you can run your own computation. It's free, so you can register, you can use it. So this is, again, the architecture of the platform besides that, but it's not, yeah, I'm not going to explain how we do it. From the users who would like to log into the platform and then provide the, let's say, and if they have any feedback. So there are some use cases. So we have a range of use cases completely different, from healthcare to food security to ocean monitoring, civil protection, forest ecosystem, and other things. But all these are completely different to show that you can use the platform for whatever reason and whatever, let's say, intention and computation specification you have. So the platform is available, and they can use it just either Google EO4EU, or you can find also the link to the platform there. I think that is all from my side. My colleague is going to take over and show you the rest. This is yours.
Thank you. Yeah, I put it aside. Can you hear me? Is it better? Yeah? Ah, yeah, okay. I didn't know that. So what I'm going to present here, my colleague Vasilis mentioned many things, including the knowledge graph. There are also some algorithms, machine learning algorithms, that were developed in the project. And the idea of these algorithms, either for image compression, so to reduce the amount of data transferred from the source to the user. And the other variant of machine learning algorithm is to reduce the amount of data that we use for downstream tasks. So we are not claiming that we are providing foundation model in the sense that they are trained on millions of data sets, but we have a specific objective in mind. So either to provide something that the user can use on their machines. So we are aiming for lightweight machine learning models that have the potential to be a foundation model if they are trained on large amount of data sets. And this is what we are going to focus on today. So lightweight machine learning model. The model that we will introduce today is called lightweight masked autoencoder for Earth observation. And it is based on mixture of experts, as we will see later during the presentation. We will go through multiple points in this exercise. So first of all, we will introduce the model, so its architecture, how it works, and the pre-training strategy, and the data set that was used for the pre-training. And then we will compare it to other machine learning models in the same area of expertise that exist in the literature, and to distinguish between this kind of model or this family of models and the models that are currently used widely in the literature. In the second point, we will go through the embedding exploration. So what we are going to do here, we are going to use the T-stochastic neighbor embedding algorithm to reduce the dimensionality of the embeddings extracted from the algorithm, and to visualize it on one of the data set, which is the Eurosat, but the Landsat version of it. And then in the third part, we will go through the expert specialization. So as I said before, this is a mixture of experts. So we have multiple experts in each layer of the model. We'll try to visualize the expertise of these experts on the image itself to see if we can distinguish between experts, for example, that are dedicated to soil land cover, or experts that are dedicated to vegetation land cover, and so on. And finally, we will apply a use case, which will be a search by image use case, where will we use the ChromaDB to implement this. So the idea is that we are going to store the embeddings extracted by the model in ChromaDB and try to do a search by image algorithm. Do you have any question so far before moving to details? So if you would like to go through the notebook with me to apply it on your side, so you can choose the PyTorch notebook on the Pangeo. Probably you don't have a lot of things to install, just 2 libraries, so it's going to be ChromaDB and Plotly that we will use. But this is one of the cells that we are going to execute. For the model itself, so there's a GitHub repository where you have all the code that will be of the model itself, and also the notebook to reproduce the experiments explained in the paper. And you have also the weights that are available on Hugging Face. So as I said before, we are aiming for lightweight models. So what we are proposing is a compact vision transformers architecture that is based on mixture of experts. So to compare in the sense of number of parameters to other models, so this model, including the encoder and decoder, it consists of only 2.5 million parameters, with 2.3 million parameters for the encoder part. So let's take a look about on the other algorithms that are used widely in the literature these days. So we have, for example, the ResNet 18, which is used in the paper called Self-Supervised Learning for Earth Observation. And it follows a convolutional network architecture. It consists of 11 million parameters. We have the 50 version ResNet, which is 25 million. We have the small vision transformer with the patch size of 16, which is 22 million. And then we have the paper, which is proposed the DOFA model in multiple versions. So the smallest one is around 100 million parameters, and then we have 300 million parameters. And then we move to the models that are produced by NASA and IBM and ESA. So some of these models, for example, PRIDVI, it arrives to 600 million parameters, and the smaller version is 100 million parameters. So if we want to tune these models, so if we are using these models, we have 2 ways to use them. So either we only freeze the features extracted from this model, so from the encoder part, and we build whatever classifier for the task in hand on top of that. But this doesn't always work, because sometimes we need to fine-tune the model. So if we have a model of such a large amount of parameters, to fine-tune it is going to be a cumbersome task, and it's not easy, especially for a lot of users who have limited amount of computation capacity. So that's why we are aiming for lightweight models for this task. So as I said before, we are not claiming at all that we are building foundation model at this phase. We are just exploring ways to introduce lightweight models that have the potential to replace heavy models as foundation models. Some of the core ideas that we use in this model, so we have sparse expert routing. So one way to reduce the computation is that the image tokens or patches, they are not routed to everywhere in the model, but they are routed to a subset of the model, so to a subset which is called the experts. So instead of routing, for example, in a layer we have 5 experts, we don't route the tokens to all the experts. So we route them to a subset of them using a routing gate. So this routing gate is going to calculate some kind of a score, and depending on that, it will route the tokens to the specific experts. And then we have also another thing, which is geotemporal conditioning, which means that if the longitude and latitude of the image that I'm using are available, and if the acquisition time is available also, I can use this as temporal as a conditioning for my input. So I can have the image itself, and I also have the metadata as input for the algorithm, which allows the algorithm to learn better in different contexts and different geographical region. And then we also use an efficient multi-head attention variant, which is a grouped query attention. So instead of having the classical attention mechanism, we have group query. We also optimize the number of parameters that we are using for the model. And finally, to reconstruct the image because this is a masked autoencoder task. So the idea is that I'm masking a lot of the input image, and I'm aiming to reconstruct this as an objective. So I'm using a lightweight decoder. The idea is that this decoder is lightweight, so we don't have a lot of learning happening in here, but most of the learning is happening at the encoder part. So if we go a little bit more in details about the architecture of this model and how the images are processed when they go inside. So imagine that we have an image. So usually the image, it has the channels. So we can have any number of channels. We will go later in the number of channels that are used for this pre-training. And we have also the metadata. So the metadata, they are the acquisition time and they are the latitude and longitude. So the idea is that we have the image, we divide it into patches. And these patches, they are then projected in the embedding dimension. And then we have also the metadata, but we have to encode these metadata in sinusoidal pairs. So for each, for example, for the week, we have 2 points representing the sinusoidal coordinates. And the same for the hour, the same for the latitude, and the same for the longitude. So after I have that, I have the image patches, and I have the encoded metadata. I'm going, first of all, to mask the input image, because as I said before, this is an autoencoder, so we are going to mask a lot of the image and then to reconstruct these masked patches at the end. So we are masking 75% of the input images, so 75% of the patches. And then what happens is that we add also a class token, and we concatenate it along with the metadata token and with the kept patches token. So we only use the kept patches, and we discard the masked ones. All of this data is then passed to the encoder. So as we can see in this part, I concatenate everything. I apply the masking, and then I pass everything to the encoder. The encoder is going to extract features, but only for the visible tokens and not for the masked ones. The output of the encoder now is 2 things. So first of all, I have the features or the embeddings, and I have also some kind of a loss. As I said before, we are using a mixture of experts, so I don't want some experts to collapse. Collapse means that no tokens are routed to them. So I want to make sure that there is balance in the distribution of the tokens along these experts. So this is the objective of this loss, is that I'm forcing the expert to have balance load of tokens. And I'm going to add this to the final training objective, as we will see later. So now I have the features of the only visible tokens. I'm going to fill this in their correct order in the input, and I'm going to fill zeros where I have the masked ones, and I'm going to pass all of this to the decoder. So now the decoder is going to reconstruct the masked patches from the visible ones, and then finally I will have the output from where I can have the loss, which is for the reconstruction loss, and I will add also the auxiliary loss, the one for the mixture of experts that allow them not to collapse. So if we look at the pre-training objective, so my main idea is that I want to reconstruct the masked tokens. So that's why I'm concentrating on the masked tokens only. So I have no weighting for this, so I'm taking the full loss that is applied to the masked tokens. And then I'm using 2 auxiliary losses. So the first one is on unmasked patches, because they exist already in the input. So probably their importance to the output is less important than the masked ones. So that's why I'm applying weighting here. And then I have the mixture of expert regularization, which is the load balancing loss that I will use. And the final loss will, for me, it will be the L masked, so in the masked tokens, and awaited unmasked loss and awaited mixture of expert loss. For the pre-training setup, so we are using the big EarthNet. So the big EarthNet originally was extracted from Sentinel-2 images, and then it was added to this patches coming from Sentinel-1. But finally, there's a version that uses Landsat to extract the same patches using approximately the same acquisition time and the same coordinates. So this data set is divided into training, validation, and split. We are using only for the pre-training the training split from that, which contains 7 spectral bands. So the spectral bands that we are using is the coastal aerosol band, the blue, the red, the green, the near, the sphere 1, and the sphere 2. So we have 7 bands. As I said before, we are applying a masking ratio of 75%. So 75% of the tokens of each image will be masked. We are training this algorithm for 500 epochs with a batch size of 128 and Adam optimizer. And we are using a cosine learn rate schedule where we have a warm-up phase of 5% of the epochs. And then we have a cosine decay with 0.05. So more details can be found here about the implementation. So if you want to apply with me, so first of all, please make sure that you have the Pangeo, no, but not Pangeo. So Pangeo and then the PyTorch kernel to be used. And we will start by installing the libraries that we'll use. So most of the things that we'll use are already available on this kernel, but we will add the ones that they do not exist. So I will run this one. So now this is installed. So going to the next step, because we are going to use Eurosat dataset for the test. So we are going, this Eurosat dataset is exists on Hugging Face. So to download it in our machine, we are going to use the git LFS, so for large files. So it is initialized. I'm going to download the dataset. So I'm cloning the dataset from Hugging Face. It's called Eurosat Landsat version. So again, the Eurosat Landsat version is very similar to what I said about the Big EarthNet. It's the Eurosat, but a Landsat version of it, where they have the 7 bands, the same bands that we used from the Big EarthNet. And we have 10 distinct classes. The dataset in general has 27,000 samples, but we are going to use only the test split, which is provided by the author. So if we check, okay, this terminal is not working. So my data set is already here. What's inside? I have the test split, the train split, and the validation split, which is provided by the original authors of the data set. And we have the data set, which is in a compressed version. So I'm going only to uncompress this file. So we can use the images inside of it after that. So each one of these folders, it corresponds to one of the classes that we have in these images. So again, this image was built with the idea for image classification, so scene classification. We have different patches, and the idea is that you want to assign a label for each of these patches. So they have 10 different classes. Some of them, they look less or more the same. Some of them, they are distinct. What we are going to do here, we are not going to do transfer learning from the embeddings, because this might take a little bit of time to train the algorithm. However, you can find these weights on the GitHub repository. You have the weights for the downstream task of classification, and you have also the weights of the model. But we are going only to check the embeddings of this data set. Okay, so this is almost done. So I usually have 10 classes, and now we have 3, 6, 8 folders. We have left 2. So it's done. So now I'm going to clone the model itself. And the repository, as I said before, it also includes the weights. And for for the time, I prepared the embeddings of the Eurosat test split, so you can download it, because maybe also extracting it directly here will take some time. So you can download it from this bucket to your local machine. And now we have everything in place, and we can continue with the code. So first of all, I'm going to import the libraries. I'm just appending the model itself, which I have here, to the path, so I can use it later. And I'm going to import some of the stuff that I'm using. So we are going to use PyTorch. We are going to use Torch Vision to perform the transforms on the dataset. We are going to use the TSNE algorithm, as I said before, for the visualization. And we are going to plot this embeddings at the end in 2D and 3D. And finally, we are going to use the expert specializations. So first of all, I'm going to get the device that we have. So if you have CUDA available, so you'll have CUDA as output here. So we have GPUs, which is a good idea for this exercise. And then I'm going to initialize the model. So what I'm saying is that I'm saying, OK, my model size, I need the small size, because we also have smaller than this. We have XS and we have XXS. The image size is 40 pixels by 40 pixels. And we need a patch size of 4, which means that we are dividing on the X by 10 and on the Y by 10. And then we have the input channels, which is 7. The checkpoint that I'm going to use, it is available with the cloned repository, which is here. I'm going to build, first of all, the encoder. And then I'm going to give the encoder to the autoencoder. I'm going to load the model to my device, which is CUDA. And then I'm going to say model.eval, because we are going to use only the model for inference and not for training or fine-tuning. This is done. If I remove this, you can check the architecture of the model. So as you can see here, we have the encoder part. And then, which the encoder part includes a multiple mixture of expert transformer layers. And we have the encoder somewhere, decoder, sorry, somewhere, which is somewhere at the end. Well, it is somewhere here, so we will find it later, or you have time, you can check. Then after that, we will set the path of the data that we will use. So we, as I said before, we are going to use only the test split of the data set. So we are going to use the Eurosat test.txt to get the IDs of these images. My data, so the images themselves, they exist on this directory, and I want this as to save some of the outputs. And then the label classes, as I see here, they are annual crop, forest, vegetation, highway, industrial, pasture, permanent crop, residential, river, and sea lake. So now let's get our embeddings, so the ones that we downloaded from the bucket. You can still reproduce the same thing from the code in this repository without any problem. You can find a notebook where you can reproduce these features. I'm going to load the MPZ array, which consists of my embeddings themselves and the labels that are associated with these samples. So we do this way. I forgot to do this. So now it's done. And then we need to check the tokens. So as I said before, we have the embeddings, but from the input, we have the metadata tokens. So these tokens, they are from 0 to 576. And then we have the class token, which is from 576 to 720. Why this is? Because my embedding dimension is 144. So if I multiply 4 by 144, I will have this number. If I apply 4 by 144 to 5 by 144, I will have this number. And then the other tokens, so the patch tokens, they are available from 720 until the end. Let's do this, and we will find that my metadata tokens, my class tokens, they are of this dimension. So I have 5,400 samples and 144 features. My other tokens, so for all the patches of the images, they are 14,400. And then if I am talking about all my text tests, so all the embedding dimension, including the metadata, the class tokens, and the image tokens, they are 15,120. Now I will apply the TSNE. So again, this algorithm is a nonlinear algorithm for dimensionality reduction. So it is used to visualize high-dimensional data sets in 3D or in 2D space. I apply, first of all, to all my embedding space. So I'm using the class token, the image token, the metadata token, and I will see what's going to happen. And then I'm going to apply this only on the image tokens, and then I'm applying this to the class token, and applying this to the metadata token, and I'm going to visualize that and compare between them. So do you have any questions so far before moving on, until this is done running? Do you have any issue with running the code, if you are running it? You don't have GPU nodes? I can stop and use my machine if you want to, yes. It should also work with non-GPU. Yeah, because everything is already calculated. It might take like a second or two longer, but... So my first one on all the embeddings is done. I'm going to do this on the image embeddings, and then on the class tokens, up, and then finally on the metadata tokens. And then we will plot. This might take some time. Let's wait until it's done with all the computation. So please note that if you run this on your machine, or you run it here, or you run it somewhere else, the final visualization that we will have here might change, because we have different versions of sklearn with slight changes in the implementation, which might affect that. Yeah, but because of the different versions. Yeah. If you fix the random state, no. But if you do use different versions, it will. I think they have, even then the parameters of the TSNE, they change from version to another. I have no idea what they have done behind. I didn't check, to be honest. It should be the same, yeah. Less or more should be the same. So now we are plotting, and let's check. So you can see that here we have this way. If I'm looking, for example, on my machine, no, it's here. And I think it's the same version. It's just installed on Mac and I imagine Linux. See, I have this one here. and you can check the first one here, which is totally different. So the first one, we have all the embeddings. The second one, we have only the embeddings coming from the image patches, and then we have the class tokens, and then we have the metadata tokens. So we can see that, for example, with the class tokens, we can have better visualization, which is can be explainable. But if we look, for example, at the results coming from building a linear prop, so we are using linear regression on top of these features, we can see that it is here. So for example here, when I'm using the all tokens, so the first one, which doesn't look very beautiful as we can see in here, it has better results than only using class tokens. The overall accuracy, the precision, the recall, the F1 score, they are much better. So visualization is an indication, but doesn't mean that it's going to be better if I'm going to build my downstream task on top of the features. So the first thing that we are going to do when we are fine-tuning or building on top of that is to use all the embeddings, and then we can use, of course, the class token for visualization purposes, but better to use all the embeddings if we are going to use this model for a downstream task. So I'm going to visualize the same thing also in 3D, but using Plotly. Which didn't happen because I'm on Jupyter Notebook. Didn't show. Well, I can show you here. So if you manage to plot in 3D, you have just to put the adapted rendering the mode for Jupyter Notebook. So you can see that, as I said before, like we have the first one, we have all class tokens, and then we have the class tokens. As we can see here, we can see in 3D we have also better distinction between the different classes. Each color represents a different class from the data set. So if I'm going to remove, for example, okay, I'm going to keep the sea, lake, and river. I'm going to remove everything else. So these two groups, they are the river and sea, lake. And then I'm going to have residential and industrial. Of course, there is some overlap because from the nature of land cover, we have a similar characteristic for both classes. We can compare the different classes. As we can see in here, we have forest, we have vegetation, so are close. If we add river to that and sea lake, they are a little bit further than this. So this is the first part of the exercise. So we were exploring the embeddings extracted from this model. And visually, so as we have done in the two exercises in 2D and 3D, and then we talked about when we are going to do this in a downstream task, it's better first to explore how to use all the tokens, and then we see if the class token or doing some kind of pooling is better adapted for our task. But from experiments on this data set, we found that using all tokens without even any kind of pooling, averaging, or whatever you want to do is better for all the metrics that we are going to calculate, like F1 score, recall, precision, and overall accuracy. Now in the second part, we are going to check the expert specialization. So this is a mixture of experts. We want to see if there is any semantic meaning of these experts. The easiest thing always to do that is to do this on the first layer. But of course, you can go deeper in the model to explore how each expert is specialized in a different land cover or a different characteristic of the image. For this exercise, we are going only to stick to the first layer. So first of all, we are going to prepare the dataset and the transformation on this dataset. So the transformation, we are going to resize the image into size of 40 by 40 as the model is expecting. We are going to z-score normalize the image using the mean and the standard deviation. And we prepare the dataset and the data loader. And I'm going to get a sample from this dataset. So in the Geo MOE MAE repository, you have some ad hoc code that allows you to do some ablation study on the model itself. One of the experiments that we are going to use is this kind of specialization of experts. So we are going to do different things. First of all, to explore the number of tokens that are routed to each expert in a specific layer, and then to show the top one expert for each patch overlaid on the image itself, and then to show the contribution of each expert to the activation of this layer. And then the final thing is to see what happens to the activation of this layer if we stop this expert. So what you are seeing here is the activation of the layer when everything is working, minus the activation of the layer when this specific expert is not working. So let's do that. I'm going to give to this code, as I said before, which allows you to run this ablation study, the image index, so which just an index of an image that I want to visualize. The layer index, so I said before, we are going to use the first layer because it's the easiest to visualize, but you can expert with anything that you want. And there are some things that I'm going to use for visualization. So for example, I'm saying that my red, green, blue bands, they are in 3, 2, 1. My max values that I'm going to use for the visualization, so I can normalize between 0 and 1, they are this one, and so on. So I'm running this. So first thing, I'm checking that my image that I'm visualizing, its class is annual crop. The distribution of expert for this image, for this batch of images, not just only for this image, I have for the first expert a mean of 100 tokens, and then for expert 1 I have less tokens routed to it, and then for the last expert I have around 70 experts routed to it. And then let's check the visualization. So in the first layer we have only 3 experts. As we can see here, expert 0 is mostly specialized in areas where I have vegetation patches. So this is vegetation. Where I have homogeneous vegetation, I have expert 0 there. And when I have either mixed patches, as I see in here, or patches that are only consisting of soil, I have expert 2 coming into play, as we can see from the, this visualization. So I go one step further, and I want to see the contribution of each patch. So we were saying that expert 2 has a visualization of soil. So if we look at the soil, we can see that the most activation is happening in expert 2 for this soil part. And we have also 0 contribution for this one, as we can see here. So we already checked here. We don't have expert 1 anywhere. And this is confirmed from this contribution. And then we can see that, OK, expert 0 is contributing to mostly everything. But we have more contribution coming to the soil from expert 2. Now I'm going to visualize another sample. So let's say I'm going to take this one. So now this confirms what happened before. When we have only vegetation masks, we have expert 0 that's coming to play. When we have mixed or soil, we have expert 2, and expert 1 is not happening because there is nothing that he's specialized on. Let's see if we have something else where we can see expert 1. So here I have expert 1. First of all, let's check what is the class. My class is sea lake, which means it's water land cover. My expert 1 that is used everywhere here because it's all homogeneous, it's expert 1. So I can see that it is specialized on water land cover. going to check something else. 15, we have also class sea lake. So we can see everywhere that we have water, we have expert 1 as a top 1 expert. Where we have vegetation, we have expert 0, and where we have mixed patches, we have expert 2. And this confirms also what happened before. So let's check one different layer. So let's check, for example, layer 5. So on layer 5, we have more experts. As I said before, like when we go deeper in the model, the kind of specialization will be harder to understand because at the beginning we have high-level features that are going to be learned, and then we go deeper, we have more specialized features, but you can still expert with that. So we have here 5 experts. If we go deeper, we have more experts. As we can see here, we have 5 experts from E0 to E4. We can see that, for example, like some kind of patches, we have specialization for one of the experts, but not the others. And then you can see the different contribution of these experts to the output. I don't know why this notebook is doing this way. Okay. So you can please go on and explore if you would like after that. And now we will move to the final part. Do you have any question before moving to the image search? All is good? Okay. So we are going to build some code that will allow us to search for images using an image. So we are going to use for that ChromaDB. You can use any vector or embedding dataset that you would like, but I'm using this for its easiness. We are going to declare some variables, so I'm going to use mean, standard deviation, and max for visualization. I'm going to use the embedding dataset that we have used in our previous exercise, the class labels also. And then what I'm going to do, first of all, I'm going to to normalize my dataset. So I'm going to use L2 normalization. And why is that? Because I'm going to use cosine metric as a metric to search for similar images. So when I'm using cosine metric, it's better to use L2 normalization. If you are using Euclidean distance, it's better to use L1 normalization, and so on. It depends on what you are going to use. The normalization can be less or more adapted. And then what I'm going to do is that I'm going to create an in-memory database using ChromaDB. So I'm saying that I'm creating a thermal client from client ChromaDB, and inside I'm creating a collection. I'm calling it image embeddings demo, and I'm instructing my ChromaDB database of how the something small word index is going to work. So I'm saying that I'm going to use a space metric, as I'm seeing here. And then what kind of metric I'm going to use? I'm going to use the cosine metric to search for similar images. So this is just some code. So if you have existing dataset, it will clean it and recreate it, so you won't have a problem. And inside the collection, I'm going to store my embeddings, and any other metadata that you want to add, you can add it inside. And let's run this cell. Okay, test. Because I run it multiple times, let me do it one again. think I deleted something now just by mistake. I'll do some Control Z. Yeah, I deleted this one. So now it's going to take just some time. As I said before, we are going only to normalize the feature using L2 normalization, and then we are going to create the ChromaDB and inside a collection and store the embeddings inside. And at the end, I have a message that I have loaded 5,400 vectors into my in-memory, so ephemeral chroma collection. And then after that, we have some code. So what this code is doing, we have a query function. So this function, it takes a vector, so an embedding vector, and then it have the top k neighbors that I'm going to return, and it's going to perform a query for me. So I'm going to take this embedding, I'm going to search my collection for the 5 nearest neighbors, for example, or 3 or 6 or whatever I want to do, and then I'm going to return that. I created some also auxiliary function that will allow me to search by index from my data set, or if I have an embedding vector, to search by this embedding vector, and this also some auxiliary function to allow me to plot my results for visualization. And let's see some of the results. So for example, I'm going to search by index my 312. I'm checking the returned results, so I have the rank, the ID of the image that's returned. So it's normal that the first one is the same image because the distance between the image and itself is 0. And then I have the other images and the distance between the image that I'm searching and these nearest neighbors. Let's visualize, which will be maybe better. So let's check. This is the image, the first one to the left on the top row is the image that I'm using for the search. And its class is annual crop. And then the one next to it is the same image because it also exists in the database. And then we have the closest images. So this one is the closest one to it, and then next one, and so on. You have, on top of each plot, we have the distance between the image and the neighbor. So it is mostly we have annual crops. We have some other kind of vegetation, which is normal because, as I said before, this is image search and not a classification or any kind of segmentation. So most of the things that are returned, they belong to the vegetation class. They are either the same class, annual crop, or something close to that, permanent crop or other kind of vegetation. But if we look at the land cover itself, it's very close to this. Again, because what we have here is that we have embeddings that represent the whole image. So it's normal that we have this kind of behavior. Let's check another example. And this one, the input image is of class river. And if we look at this kind of geometry of this river, so we can see that regarding the image, it's not that big. It crosses the image in this direction. So we can see that all the returned images also, they are river class, first of all, and they look very similar in terms of like the geometry of this river, how it looks like. Because if we look later, for example, to this one, it's also a river class, but we can see that this river is much wider than the one that we have before. So it goes almost from the top to the bottom of the image. And that's also explains why we have some sea lake classes where we have some land appears also in the image, as we see in this patch and this patch. But we have the river, as we can see here, and most of the time we have sea lake where we have also some kind of land in the scene itself. But what if we have sea lake without anything? So we will have a result where we have only sea lake. We don't have any kind of land that appears in the scene. Going to check another image. So if we have forest, this is some kind of homogeneous land cover in all the image. We don't have any changes. So we have only forest returned. We don't have any kind of confusion. And now if I want to show an example of residential, we can have this example. So the first one, as I said before, is the image itself. And then we have the closest to it. We have annual crop, because annual crop, sometimes of the year, we have only soil. And this kind of resolution of the images, soil, and this kind of residential places where we have this red color, they are very similar. And because of the resolution of the image, also the texture is not very clear, because as I said before, we are using Landsat. But we also have some residential samples that are returned as part of the query. Let's check the last example. So about also annual crops, but this is also a different kind. So if we check this annual crop, we have only soil. And if we check this annual crop, we have mixed parcels inside, or mixed fields. We have some fields which have vegetation, and other fields which have soil. So we can see that in most of the images that are returned, we have this kind of representation of the fields. As I said before, this is query and not classification. Do you have any other question, please? Or do you have any problem running the code, or anything that's not clear? Good. So in this code, if you have here, you have the code to compute the embeddings. So there are examples to compute it from big EarthNet, as you can see in here, and you can compute it also from this Eurosat net. You have also examples of code where you can train a logistic regression on top of the frozen encoder, as you can see in this one. You can pre-train the model on your own dataset, or on different dataset, or even like change the model to a different sensor using this code. And you have the model weights available here in these folders. And finally, I want to show you the analysis tools. So it's the tools that we use for visualization of the experts. They are all available in this code. If you have any question, please do not hesitate to contact us. And thank you. All good? So we still have some time. If somebody else wants to add anything, yes, please. Mm-hmm. So for the big EarthNet, we have some effect for the so the Eurosat dataset. They don't have this kind of metadata. They don't have they have no lat long or no acquisition time. But for the big EarthNet, we have better, let's say, search results when we have this kind of metadata. First of all, because the model was trained on images with metadata. This is the first thing. But the most impact was for the tokens coming from the images itself and not for the metadata. But we also, we noticed this kind of improvement when we have metadata associated with the images rather than when we don't have metadata. But what we proved here is that even if we don't have this kind of metadata, we still can use the model, because this conditioning is optional and it's not mandatory if we don't have it. Yeah. No. They, when I told you this, it's not for search, it was more for classification. We have better. But if you are doing this kind of similarity, we will have similar land cover more than this kind of location, because it's true that adding this kind of metadata can add some bias if we have the same geolocation. But most of the weight that's in the feature is coming from the tokens and not from the metadata. Yeah, of course. This is the idea to expand this to, we say multi-sensor, but doesn't mean only sensor, but we can use, for example, something like land cover classification or elevation models or OpenStreetMaps to enhance also this. So we hope that adding this kind of modalities, we don't know yet how we are going to add this because it might also make the model larger, but the idea is we want to stay fiddle to the idea of having lightweight models and not have big models of hundreds of millions of parameters. Yeah. So we need to find a smart way to do that. And this is going to be interesting to have this kind of models where it can work if you have all the data modalities that you are using or only one of them. Because, for example, in clay model, you can, if you have Sentinel-1, Sentinel-2, and like Landsat, you can work with all of them. If you have one of them, you can work with one of them. If you have even subset of the bands of one of the sensors, you can work with this subset of the bands without using everything. So this kind of flexibility is nice to have here. So I guess that's all. I don't know if anybody else, like from Pangeo or from EO4EU, wants to add something more. No? Yeah. Yeah.
Okay, no, just a question about the infrastructure, because when trying to run this, as he said that we need to use Torch, I tried to change to the Docker file that has Torch, but there were some limitations of available nodes with GPUs and so I was not able to do that.
Yes.
This is because of the infrastructure, no? It is something that...
It's a limitation on the number of participants and the number of GPUs. Yeah, and this is why, for instance, Jean-Marc also reduced a lot his notebook to make sure we can also run it without GPUs. It's most of the time we are not like so many people at the same time trying to access the same resource. And if we really need a lot more resources, we can enter a new agreement and add more resources. But yeah, so you were hit by this lack of resource. That's the infrastructure itself.
And just also for curiosity, if at some point I am a user of this and I need to create a Docker file with my dependencies, it is possible to contact this, because I cannot add directly these Docker files to the infrastructure?
So if you remember at the very beginning when you started, you can even add your own image. So at the very beginning, you when you have the list of the different images, we have like the Pangeo notebook, the PyTorch, the TensorFlow, the data science. And you can also have like enter your own image, and you can put your Docker image or Quay image and run it. If you want others to be aware and use it on a more regular basis, you can make a pull request to the Pangeo EOS and add your image for, like, I don't know if you have a Docker image that with packages that are very useful for everyone. Yeah, please do so.
Okay, and for the for adding your own image, it is something that you have to. It has to be in Docker Hub, in a public repository.
Yeah, it has to be in a public repository. Yes, that's a constraint. Yeah.
Thank you.
Yeah. Other questions for any topics related to what we have seen this morning? Everything all fine? So you can use the infrastructure after. You have like a year subscription. And then you will receive an email saying that it will expire. So you can enroll again following the same procedure.
There is no restriction for using it for a specific research project?
Yes, you can use it for your research, not for mining or doing nasty things. We have some, like they are monitoring the infrastructure. If they see a bit odd usage, they usually contact the user and ask. But so please use it for your research. It's sponsored by Chestnut, which is in Czech Republic. And they are offering these resources free of charge for Europe. So I think we should use it wisely. But it's indeed, you can use it. Feel free to use it.
Okay, so mining should take 20%, yeah, if they run any mining algorithms, we take 20% of
Yes.
the profits.
Yeah, I take more.
20%.
I take the rest.
Yes, I take the rest. Any other questions? Comments? Feedback? And was it too fast, too short, too complicated, too simple? It's very hard for us to know because like there is a very diverse set of attendees, and it's also a bit difficult to know the level. So please give us some feedback so we know, like, for next time. So feel free. We don't take it personally. At least I don't. Yeah.
For the last one, you actually needed some AI background. Otherwise, you could not follow. And for me, I had a little bit of AI 5 years ago, so I could half follow the way through. But then, yeah, maybe either indicate that or make an introduction.
That's a good input. So maybe we also put some links for like a prerequisite for people to look at if they are not familiar.
You have, in the notebook itself, you have the links to the GitHub repository, to the paper itself, to the weights. You can also like contact us if you have any. I don't know if I have. My name is there. So my name, first name dot last name at ECMWF should be my email if you want to contact. Yeah.
But it's true for next time. We will probably try to make it clearer.
Yeah.
Any other feedback or comments? You're ready for lunch? So do you all know where to go for lunch?
Of course, no.